Hello, young chemists. Let me ask you a fun question. When you go to a shop and buy a packet of chips, do you want to know only the ratio of potatoes to oil? Or would you also like to know the actual number of chips inside? The empirical formula tells us the ratio, but the molecular formula tells us exactly how many atoms are in each molecule, like counting the chips in the bag. The molecular formula shows the actual number of atoms of each element in a compound. For example, glucose is written as C₂H₄O₄, which means 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen in every molecule. Sulfuric acid is H2SO4 with 2 hydrogens, 1 sulfur, and 4 oxygens. So, if the empirical formula is a clue, the molecular formula is the full identity card of a compound. Now, how do the two connect? Simple. The molecular formula is always an integer multiple of the empirical formula. Mathematically, we say molecular formula equals n times empirical formula. Here n is an integer, 1, 2, 3, and so on. To find n, we take the molecular weight of the compound and divide it by the empirical formula weight. If n equals 1, then the empirical and molecular formulas are the same, but if n is greater than 1, then we multiply the subscripts of the empirical formula by n to get the molecular formula. So remember, empirical tells us the proportion, molecular tells us the real count. Alright, let's treat this like a step-by-step recipe. Step 1. Calculate the empirical formula from percentage composition, just as we learned earlier. Step 2. Calculate the empirical formula weight by adding up the atomic masses. Step 3. Find the molecular weight, often given directly or calculated from vapor density. Step 4. Find n, which equals molecular weight divided by empirical weight. Step 5. Multiply the empirical formula by n to get the molecular formula. So, think of it like baking bread. First you know the ratio of flour and yeast, then you weigh them, then you check the size of the loaf, and finally, you scale the recipe up or down. Chemistry and cooking, not so different. Let's solve a real example together. We are given a compound with the following percentage composition: carbon 26.59%, hydrogen 2.22%, and oxygen 71.19%. Step 1 is to calculate the empirical formula. We divide each percentage by its atomic mass. Carbon 26.59 divided by 12 gives 2.22. Hydrogen 2.22 divided by 1 is 2.22. Oxygen 71.19 divided by 16 is 4.45. That gives a ratio of 1 is to 1 is to 2. Hence, the empirical formula is CH02. Step 2 is to calculate the empirical formula weight. For CH02, that's 12 for carbon, plus 1 for hydrogen, plus 2 times 16 for oxygen. So 12 plus 1 plus 32 equals 45. Step 3 is to find the molecular weight. If vapor density is given as 45, then molecular weight equals 2 times vapor density. So 2 times 45 equals 90. Step 4. Calculate n. Molecular weight divided by empirical weight equals 90 divided by 45, which is 2, so n equals 2. Now the last step, molecular formula equals empirical formula raised to n. That means molecular formula equals CH02 to the power of 2, which becomes C₂H₂O₄. This compound is known as oxalic acid, a common substance found in leafy vegetables like spinach. Yes, the sharp taste of spinach is partly due to oxalic acid, which we just derived by calculation. So from a table of percentages, we reached the actual molecular formula, and even connected it to what's on your plate. So why do we bother finding molecular formulas? Because they identify the complete composition of a compound. Organic chemists use them to design drugs, fertilizer companies use them to label nutrients, fuel chemists use them to analyze hydrocarbons, and polymer scientists use them to determine monomer units. Let's summarize. Steps. Percentage composition gives empirical formula. Add up atomic masses to get empirical weight. Use molecular weight or vapor density to find N. Then multiply the empirical formula by N to get the molecular formula. Remember, empirical gives the ratio, molecular gives the actual count. So next time you see a formula like C₂H₂O₄, you'll know it's more than just letters and numbers. It's the molecular fingerprint of glucose, the sugar that powers life, and that's the magic of molecular formulas. I hope you enjoyed this journey from ratios to real numbers. Catch you in the next class, where we'll keep unfolding the hidden patterns of stoichiometry.